thanks everyone for joining. And if you don't want to be recorded, you can turn off your camera. So this is our 9th Hackaday session, but also we have included other communities today, joining from every location in the world. So we'll be showing some new things and also cover some of the areas people who have been here have learned before. So if people don't mind muting themselves. And to give people an idea of the classes, it's been ongoing for quite a while with Hackaday. And every week I have some comics posted on Hackaday. This is the intro to quantum computing project. Every Sunday, I spend about 30 minutes, and now we are extending a little bit to an hour to cover one concept from theory to hardware or programming, and we can leave some time for Q&A. People can also feel free to post their questions or discussions in the chat during my presentation. I may not be able to get to it immediately, but we can look at it once I finish presenting the slides. And also, if we don't have time to cover everything, we can move all the questions to the Hackaday project, and I can reply to people online. The documentation that we've been using is based on the Microsoft documentation on Q# language, and also we use the quantum katas as our practice exercise. And if you are participating in the discussion in the chat, if you know the answers to some people's questions, please feel free to jump in and write in the chat, and feel free to discuss as a community. So welcome and welcome back to people who have been coming. We are having several communities joining from Hackaday, from Microsoft Reactor, from the Microsoft for Startups. We also have Zen for Maker Meetup group probably joining from there. Wherever you are in the world, I hope you are safe, and I'm really glad to see that this intellectual subject is bringing people from all over the world together. So just a little bit about myself, some background that I am a physicist, and I started my professional study in University of Cambridge, and I did condensed matter physics and work in the labs on low temperature physics and optoelectronics, built a lot of equipment, and did experiments on the fundamental properties of materials, so studying quantum matters. And then I went to Harvard for my PhD, working on plasmonic circuits. Went to the clean room and fabricated chip structures, designed them, and did a whole kind of inventing the chip structures from scratch to producing them and doing experiments on them. And then I went to Intel to work on silicon photonics, which is the interconnect that you need in data centers between optical fibers and servers. And I also worked on those Maker projects and hardware, and did UX design, and did a lot of wearable projects. So that was really fun. And then I went to Microsoft as a manager of the Garage Innovation Program. So there I was able to pursue some of the intersections between science, engineering, design, and art, and also supporting our employees to pursue their areas of interest. And that's when I then started going back to quantum physics, so it's always been quantum physics, but really that's started looking at quantum computing when I was in the garage. And even though I had a PhD in physics, it didn't mean that I knew much about quantum computing. So that was a really interesting area for me. I started learning about it myself, and then I started teaching our employees just learned with everyone and learn from our experts. And then I joined the, in between, actually, I also have a fashion brand that I do wearables and fashion design with science, combination between science and art as the theme. Now I'm with the quantum computing team officially at Microsoft, where I support the education and lead the education effort globally, and given people the materials producing education content to support our customers and hobbyists and students, anyone who needs to learn about quantum computing with the appropriate content. So this classes is kind of my personal effort to also drive the community, providing the fundamental scientific literacy on this subject. There are some of the global goals that I'm personally interested in pursuing beside my day job. So giving quality education and helping people understand what quantum computing really is one of my goals. So at work, I produce these learning materials. I manage the Microsoft documentation and also produce these learning paths for people coming from different backgrounds. Recently, we launched these 2 Microsoft Learn modules. One is to help you get started with coding with Q#, using the quantum development kit, and also a module on solving optimization problems using quantum-inspired optimization. So check those 2 out. And especially when we get to the coding part, the first module would be very directly relevant. This project with studying quantum computing through comics is kind of my personal interest when I started just when we started working from home. And I thought that I wanted to improve my own understanding of all the quantum subjects, quantum computing areas, and also be able to use an accessible way to communicate to people. Because I like drawing, it just naturally came to me. I wanted to use comics to teach. Ever since I started teaching, and it's been really well received by the communities. And I would like to do is also to show people what is really quantum computing and what does it involve beyond a lot of the basics that media talks about. And we need to get to the level that we need to have a understanding of the basis that quantum computing is using from quantum mechanics, namely superposition, interference, and entanglement. So those are the 3 theoretical topics that we need to have a good grasp on. Then there's how do you use it for programming, and that relies on linear algebra. However, we don't have to be an expert in linear algebra. It just requires us to do a little bit of math, and then we'll be able to program in algorithms. And eventually, you would need to write programs that would run on actual quantum hardware. And that's what I think can be taught through coding and also having hands-on practices to connect all of these areas together. One tip I would give people about getting to learn quantum on your own is identifying what is a good source. There are a lot of really great content online, but there are also a lot of, I said here, BS.
You did or you didn't?
So can someone who's speaking mute themselves? Thanks. So if you see materials that talks beyond these superposition and entanglement and start giving you ideas of algorithms, those tend to be good materials that they are developed and they move forward. Those materials that only is staying at explaining incorrectly what superposition and entanglements are, those tend not to be worth reading. So that's a tip I would like to give people. And most of these materials don't even explain what interference is. So we're gonna talk about all of these and debunk some of the misunderstandings that's commonly spread in media. So people who have been coming to this class have already seen these algorithms. They have learned about quantum oracles, Deutsch algorithms, Deutsch-Hose algorithm, and Groover's algorithm. I will also like to show a lot more beyond those. There's Shor's algorithm, there are chemistry simulations, there's quantum machine learning, which is a super hyped area as well. There's also what is quantum inspired optimization, and also how do we program a hardware that, because that's what we eventually will get to, is understanding how quantum computing works. And we can run them on simulators, but we will also eventually use quantum computers and hardware to do the programming. And if you are an expert in any of the subfields in quantum computing, let me know. And we would love to have you give a guest lecture if you are doing quantum computing already full time. So in terms of understanding, especially for physics related subjects, quantum computing is one, of course. I think there is a trinity for learning and understanding. We need to be able to describe things with words, and we need to be able to use equations to describe the system. You need to be able to use pictures to condense the words. And all these three, you can overlap and they can replace each other interchangeably. When we get to that point, that is how we can reach real understanding. We have to be able to translate between these areas. And that's what I try to show in the class, is to use more words and drawings to describe them. And I have avoided showing too many equations to make it more accessible. But we can use coding to give people some hands-on practice that would also enhance with our math understanding. So for today's class, we're gonna start from superposition, but we're not just gonna stay there. We actually going to take this, I drew this from mountain to mountain, these cable cars that's labeled as Q#, which is a quantum language that Microsoft invented. We're gonna use that as our tool to go from a fundamental concept to a practical area. How do we manipulate our system to writing some very, very simple algorithms? It will get much deeper, but today we're gonna just do an introduction and do something very straightforward, but explain what superposition means first. And we'll also explain the other concepts in future classes. A step back is to see the importance of computing. Everyone knows that all of our world, things, and people are connected with electronics and computers, with data centers. We cannot live without computers anymore. We run a lot of very hardcore tasks on supercomputers. However, there are still areas that our most powerful supercomputers can still run into fundamental limitations. Things like chemistry simulations and material discovery, those are fundamentally quantum mechanical interactions in those materials. we cannot go beyond a certain complexity of the quantum mechanical interactions using our current computing method. And there are areas that's like signal processing, logistics, cryptography, information security. Those are algorithms and methods that we came up with. They are not fundamentally quantum mechanical, but we can use quantum methods to get more efficient applications in these areas. So quantum computing holds a lot of potential to solve problems that our current quantum computers cannot solve. It doesn't mean that quantum computers are better for everything than classical computers. They're very specific for specific tasks that are suitable for quantum algorithms. And really, quantum computing is like biomimicking, is like a lot of the other inventions that we have as humans is learning from nature and implementing that in engineering. Quantum computing is the same. We are learning from how fundamentally our matters work. The smallest molecules and fundamental particles like electrons, photons, how do they interact and how can we use their behaviors in computing? That is what this field is about. So our current electronics are based on transistors, which use the zeros and ones as the information bits. And they are basically like small switches, and these are binary systems. We can have all kinds of counting systems. We can use number 10, we can use 12. There's not really a restriction on what we can use to count information, but then we resolve down to binary, and all of our electronics is based on zeros and ones. So classical bits is like very simple setup where you can describe your system as a switch that goes on or off. So you can label that as 0 or 1, or temperature being too high or too low. You can also make it binary. Or if you flip a coin, you can have a head or tail. So those can all be analogies of binary systems. Mathematically, you can just describe them using these vectors. Those are our bases for 0 and 1. And if you look at this, it only has two numbers, and that's the only options that we have if we have only 0 and 1. So if you use vectors to describe 0 will be 1, 0, and 1 will be 0, 1. Now, if you have multiple bits, we're still talking about classical bits. You can combine them using this tensor product or Kronecker product. Given how you define it, you can define it to lay out this way. If you have two bits, you will only have 4 options because you will have 0, 0, 0, 1, 1, 0, and 1, 1. And you can describe them as these tensor products of 2 independent bits. These are just 2 vectors, and then you will obtain a 4x1 vector for each combination. So in total, you will have these 4 options. And you think about it, yeah, that's what it makes sense. If you have 4 options, then you would have these 4x1 vectors, each with a 1 in it, and the rest will be 0, and they are in this order. Mathematically, you can calculate what the tensor product is So I would recommend people take notes during the class as well. We're gonna show some of the ways that we calculate. So a tensor product is nothing but just trying to represent two bits together, and is just the first element times the whole vector and the second element times the whole vector, and then each timing each. So you'll get all these combinations out. If you have multiple bits, you can keep doing the tensor products and writing really long vectors. So say if you have a 4 in binary, you would represent it with 1, 0, 0. So then you would do a tensor product of these 3 bits. Then this is how you would represent a 4 in a vector. We're still talking about classical bits, and to implement that in hardware, we use transistors. That is basically a sandwich of semiconductors with metal gates and insulators. You can form these regions that's filled with electrons, mostly positive or negative charges. And then if there's electricity from source to drain, you can control that with the gate, how much electricity you want that electrical current to flow. If there is electricity, then you can call it on, so that's a 1. If there's no electricity, you can call it 0 to be your off state. So transistors are tiny, tiny switches that we put in our chips in the computers. That's how we implement classical bits. But this is kind of fictitious and deliberately artificial. Nature doesn't behave this way. Nature is made of matters like atoms, electrons, photons. They have discrete energy levels, and they can have all these levels all be in a superposition. And I will explain what that is. And these discrete energy states are the quanta, so that each energy level can be described as a quanta. That's why we're calling this quantum computing, because we're utilizing the quanta, how nature intrinsically behave, and we are imitating that in computation. So what we need to have is any system that can give us some superposition of different energy levels or different states. How would that work? And what is really a quantum bit? So classically, say you can use any binary to define your classical bits. If you say have a circle that is empty, you can call it 0. If it's filled, you can call it 1. But then in the quantum system, you could have them in superposition, which means you can have one circle, but then you have a probability of having it filled and another probability of having it empty. Then you see, okay, I, in this case, have 1/3 of 0 and 2/3 of 1. You can use some other analogy, like a lottery bowl that has 20 beads. You can say if they're all red, you can have 0. If they're all blue, that's a 1. But if you have a mix, you can have 8/20 chance of getting 0 and 12 out of 20 being 1. Using a coin, you can say a head is a 0, a tail is a 1. You can just arbitrarily label them. If it's an even coin, you will get 50% chance of landing on 0 and 50% chance of landing on 1. That is what a qubit does. It is given a linear combination of all the possibilities. Each possibility has a certain chance, certain probability labeled. So that is superposition. You may have heard very often in the media a superposition is 0 and 1 at the same time. What does that really mean? It doesn't explain anything. And what's timing here? There's no parameter called time. That's a really wrong description. So if you hear them say that, that's just take it as a grain of salt, and you can stop watching them. So mathematically, how you can represent that is also using a vector. This is any arbitrary label. Phi is, you can say this is a quantum state and it's described by a vector. But now, instead of just 0 and 1, you can have any arbitrary number to give a weight to these 0 and 1 possible states. So A is the amplitude of state 0, and B is the amplitude of state 1. The probability of the whole system of being in 0 is given by these amplitudes. A for 0, and A squared is the probability of the state being in 0. B squared is the probability of the state being in 1. And those two are all both possible outcomes, possible states that this quantum system, qubit, can be in. And A and B can be any number. These are amplitudes. They can be positive, can be negative, or they can be complex numbers. And this is very significant later on when we talk about interference. That becomes very useful. So for now, you will just see that, okay, A and B are two amplitudes, and all we need to make sure is that their probability adding up will be 1. This makes sense. Like in any system, just our daily life, anything's probability cannot be larger than 1. So the amplitude squared is the probability. The sum of them will be 1. So in our early example, our circle will have an A square of 1/3 and a B square of 2/3. Similar with the beads, you can get the probabilities of these two possible outcomes. If you have multiple qubits, say you have 2 qubits, you do the same thing like classically doing a tensor product. You just have these arbitrary amplitudes in front of them, and you will get these 4x1 vectors again. So each is an amplitude of these 4 possible states. So remember our earlier introduction of the 0, 0, 0, 1, 1, 0, and 1, 1. We have 0, 0 being 1, 0, 0, 0. So that's this one here. So that the other 3 elements were all 0, but you have this AC left. So you can label them like these superposition of the 4 possible states. Again, you don't have any restrictions on the sign of whether they're real numbers or complex numbers. You just need to make sure that they add up to 1, the probabilities. So looking at the difference between classical bits and qubits again, mathematically you can write a classical bit as 0 and 1, and qubit is just a linear combination of the 2 possible states, each with an amplitude associated with them. And the amplitude square is the probability. Then what does this lead to? If you have a qubit, you know you have these 2 possible configurations. If you have 2 qubits, you have 4 possible combinations. If you have 3 qubits, then you can write out all of these possible combinations, and you see that's 8 of them. So n qubits will give you 2 to the n possible configurations in superposition. That's what's really cool about qubits. is that the number of possible configurations is grows exponentially with your number of qubits. And it doesn't just grow as 2 to the n. The possible combinations of amplitudes is infinite. We already mentioned that they can be any number as long as you guarantee that the probability sum equal to 1. So your state, you can describe all these superposition or linear combination of the possible states into a sum of each possible state. And these amplitudes here can be positive number 1, 1 over 2, 1 over 3. They could be negative, just put negative on them because it doesn't matter when it's squared, it's positive and probability is positive. They can be imaginary, so you can put an I in them. So in general, they can be complex. We'll talk about the consequence next time. So we have very quickly covered what superposition really means. And now you have a qubit. How is it going to be used? We need to be able to manipulate it. And how do we do that is to use linear algebra. And that name may sound too heavy, but is nothing but some matrices that could be applied to vectors to change your vectors. So remember, we have these states that is a vector and you have some amplitudes associated with them. There is a very commonly used gate called the H gate or Hadamard gate. It has this kind of form. What it does is applying these 4 elements onto the vector. So is a 2 by 2 matrix is to change at first, you can say at first it's classical, but then you apply a Hadamard gate or H gate to them, it will become a superposition. It will become a combination of 0 and 1. If you start with 0, that's a special case in a qubit, which is the same as a classical bit. You get this into a superposition state that also has a 1 in it. If you start with 1, you do a Hadamard gate, you will also get a superposition between 0 and 1, but this time with a negative sign. So that's why is almost all of the elements could be the same except this last minus sign here, which is very important because it makes sure that when you get these plus and minus states, you can do another application on these plus and minus to return to 0 and 1. If you don't have this minus sign here, you wouldn't be able to return and distinguish your states. You can imagine that is because it's a vector here, you could represent your vectors in a 3-dimensional space using a sphere. This sphere actually has a name called block sphere, but don't worry about it for now because we're going to talk a lot more next time. You could label your 0 and 1 as these polar positions on this sphere. And what this Hadamard gate does is to put your original state into these perpendicular locations that are in between 0 and 1. So the plus and minus states are just superpositions of 0 and 1 with an equal amplitude. So it's right in between the two. That's what Hadamard gate does. And there are other commonly used gates. We would talk a lot more about gates, but I would like to show you some very simple ones first. There's another set of gates that's called polygates. You don't have to pay too much attention to the sphere yet, because I will explain them more in detail. you can just look at the form of this 2x2 matrix. X gate does nothing but to flip the positions of these amplitudes. So if you start with 0, an X gate will make it a 1. If you start with 1, an X gate will make it a 0. So it basically does a flip. I think in classical computing, you also have this flip gates. And you can also have a Y that's just very similar, but adding some faces to it. There's also a Z gate that is almost a identity matrix, which does nothing to your system, but then the Z gate has minus sign here, so it adds a minus sign to your second element. So these are some of very commonly used gates. And if you want to look at the sphere, a Z gate is basically rotating your vector around the Z axis, and X gate is rotating around the X axis. The Y gate is actually a combination of X and Z, so you actually just need the X and Z. You don't need the Y gate. But I will show you more about the block sphere next time. Don't worry about it. So we have learned a little bit about how to change your quantum bit, and we learned what superposition means. And now we can go fast forward to do some coding to see how things would behave.